And we can actually calculate the energy changes that occur on each portion of this particular graph. And we would do this in the following way. Here, we would use, since there's a temperature change going on, we would use Q equals the mass, which is just a gram, times the specific heat of solid water, so that would be the specific heat of ice, times the change in temperature. So let's do that. Let's calculate what the energy change would be to take ice at 0 Celsius and warm it to, at 0 Kelvin and warm it to 273 Kelvin. So we can do that. Q is going to be 1 gram times the specific heat of ice, which is about 2, let me just see, I think it's 2. That's per gram joule per melting of water. I don't have it listed, but I think it's, yeah, it's about 2 joules per gram per degree Celsius. I guess we're going to find out if it's right. I'll be able to tell on the chart. Times the change in temperature, which is going to be 273 Kelvin minus 0 Kelvin. Final temperature, initial temperature. So what's that come out to? Uh-oh, my kelvins aren't talking to my Celsius. That's fine. We'll get that in a second. So Q is going to be 1 gram times 2 joules per gram per degree Celsius times, that minus that, is 273 Kelvin. Okay. 273. Oh, wait. I got to do this. Hold on. We better do this conversion prior to doing the calculation there. So let's see. 273 Kelvin, that's 0 degrees Celsius, correct? Yep. And then minus a 0 Kelvin, which is negative 273 Kelvin. So we're going to add those, of course. This should be Celsius. Yep, that converted to Celsius is that. We add those together, we're going to get a positive 273 degrees Celsius. There we have it. So let's see, I take 1 gram, multiply that by an inverse gram, those will cancel. Degrees Celsius and degrees Celsius, those will cancel. My unit I'm left with is joules, so it's basically going to be 2 times 273. That's going to be 546 joules to get me from here to here. And if I look at my chart, that matches up pretty well. It takes that much energy to get me from here, to get the temperature to go from here to here. It takes about 546 joules of energy. Now we're going to calculate how much energy it takes to go through this step, the melting step. Well, that's going to be different. The reason why that's different is there's no change in temperature here. No change in temperature, so I can't use Q equals mc delta T. What I'll do for this step, Q for the phase change, which is melting, I'm going to take the mass of water, which is 1 gram, and I'm going to multiply that by the enthalpy change for the melting of water, which if I go back to slide number 16, the enthalpy change for the melting of water is 333 joules per gram. Well, that's pretty easy. 333 joules for every gram. That cancels that. It's 333 joules. So to go across this portion of the graph, it's going to be 333 joules. So what's that, about 540 and another 330? We should be about 900 right here total. And if I look at the graph, that's about right. We're a little shy of 1,000 right here. Now for this portion of the curve, we have a place where we're warming liquid water. So, and the water's obviously increasing in temperature. So in this case, for this portion of the graph, I'm going to use Q equals mc delta T, where this is the mass of water, this is the specific heat of liquid water, and this is the change in temperature that the water undergoes. So let's see, Q is my mass, which again is just a 1 gram, times the specific heat of water. We know what that is, 4.18 joules for every gram for every degree Celsius, times the change in temperature, which is 373 Kelvin, that's 100 degrees Celsius, minus 273 Kelvin, which is 0 degrees Celsius. And I'm doing this conversion here so the units talk to each other. And if we run that calculation, well, this is going to come out to 100 Celsius here. Degrees Celsius cancels inverse Celsius, inverse gram cancels gram, and I have 4.18 times 100, which is 418 joules. So to get me from here to here, it's going to cost me 418 joules. So let's see. This first step cost me 330. This second step cost me an additional, what was it? Got me to about 900. I don't remember exactly, what was that, 540 or something like that. That got me to almost 900. And then if we add an additional 400 to 900, to get to this point here, adding all these up, the energies for this point, this should be roughly 1,300. And if I look on my graph, I can see I'm a little shy of 1,500. So this is making sense. Now for this step, the boiling of water, that's going to take a lot of energy. I can see it. I mean, that's a really long line there. But with all this energy gain, there's no increase in temperature. So I can't use this equation. For this, I got to use the enthalpy change for the phase change. So for this step, going from here to here, I take the enthalpy change for vaporization. That's going to be how much mass I'm vaporizing, which is 1 gram. And if you look at slide 16, it's 2,258 joules to evaporate a gram of water, and that's pretty easy. You do the multiplication, these cancel, and this step is going to require, wow, 2,258 joules of energy. That's why that line is so long. And then finally, for the last step, for this part, we would have to determine how high we're going to heat it. We're not going to do that, but if we were going to calculate it for this last step, we would say Q for that last step is going to be the mass of water, again, which is 1 gram, times, in this case, the specific heat of steam, times whatever change in temperature the steam would have undergone.